Hey there! In this math lesson, we're going to be doing probability. So probability is the likelihood of an event happening or not. This means we are measuring chances. Probability figures always lie between 0 and 1. Events whose occurrence is obvious and 100% guaranteed have a probability of 1. Such events definitely happen without fail. For example, my probability of dying is 1. At some point, I will die, and there are no two ways about it. Events which are definitely impossible have a probability of 0. Such events will never happen, come what may. The probability of a man to get pregnant is 0. The probability of cows to fly is also 0. But wait, what about those events that could happen or not happen? Because they have a probability of neither 0 or 1, they are somewhere in between the two, and that makes them fractions. There are two types of probability, and these depend on the manner in which we determine the probability of any event. We're going to delve deeper into each of them. Experimental probability involves finding the probability by practically acting out whatever event whose probability we need to determine. This gives us a number of times an event happens as well as the number of times it does not. If I drop a sharpened pencil on the floor 10 times, with the goal of finding the probability of the pencil's tip to break, I'll achieve that goal by making the number of times the tip broke a fraction of 20. That is how we get the general formula. Now we're going to move on to the practical examples in daily life that we can quantify. Now here's a die. A die is a cube with each of its faces marked with dots to represent the numbers 1 to 6 that resonate with the 6 faces. When we have more than one, we call them dice. Dice are rolled and tossed in gaming to get an outcome between 1 and 6 inclusive by counting the number of dots on the face of the cube that will be facing up. The probability of getting a 1 is 1 out of 6 because there is only one of the 6 faces that has one dot. The same applies to all the other numbers. Another case where we find probability is that of coins, because when you toss a coin, there are two available outcomes. It's either we get a head, which is the side of the coin with the face, or we get a tail. So the probability of getting a head is 1 out of 2, and the probability of getting a tail is also half. Playing cards are also used in studying probability in mathematics. Each set is made up of 52 cards, and each of those cards belongs to a set: hearts, diamonds, spades, or clubs. Pause the video here and take note of the 13 cards that belong to each set. You can have a look at this illustration of a set of cards. We can also obtain theoretical probability figures from spinners. A spinner is made by inserting a pointed matchstick in a regular polygon through its center. It is used to determine an outcome, especially in gaming. Each of the sides of the polygon is labeled so that we can distinguish one outcome from the other. In this case, we have an octagonal spinner, but it could be triangular, pentagonal, hexagonal, or so forth. The spinner is set in motion by twisting the stick between the finger and the thumb such that it spins and comes to rest with one end lying on the surface. Now that we have a clear understanding of probability, we can get practical with it. Here we have 10 balls with us. Given that they are placed in a box and a person is asked to pick them randomly, we need to determine the probability of picking each color. Now, instead of writing the probability of picking a red ball is 3, here is what we write. R to represent red is equal to 3. So the same applies to white. PW is equal to 4. Then all this is out of 10 because probability is from 0 to 1. At the same time, we use a grid to determine the theoretical probability. For example, when you toss 2 coins, the possible outcomes for each coin, this would be coin 1 and coin 2. The possible outcomes for each coin would be head and tail, head and tail. So this outcome would be head and head. This one would be head and tail. This one would be head and tail. This one would be tail and tail. So that means that the probability of getting a head and a tail is half. The probability of getting 2 heads is a quarter. The probability of getting 2 tails is also a quarter. Or is that of a pentagonal spinner spun and a coin toss at the same time. So for a spinner, which is the side, since it's pentagonal, it's up to 5. Then our coin, is its 2 obvious outcomes, the head and the tail. So this is 1 and the head, 2 and the head, 3 and the head, 4 and a head, 5 and a head. 1 and a tail, 2 and a tail, 3 and a tail, 4 and a tail, 5 and a tail. So the probability of getting let's say 2 and a head would be 1 out of 12, because in this case, 1 out of 10, because in this case we have 10 possible outcomes. The probability of getting a multiple of 2 and a tail would be, these are the 2 out of 10, because these are the 2 multiples of 2 and they are combined with the tail. Now we'll move on to the section of tree diagrams. A tree diagram is used to illustrate successive events as they branch out from each other, as shown in this picture. Now let's say we have a bag with 10 balls, 7 are yellow and 3 are green, and 1 ball is picked after the other. When we first pick, our likelihood of getting a green ball would be 3 out of 10, while our likelihood of getting a yellow ball would be 7 out of 10. But when we make our second pick, the probability is no longer out of 10 but out of 9, because we already lost 1 ball. So the probability of picking a yellow ball after picking another yellow ball would be 6 out of 9. And the probability of picking a green ball after picking a yellow ball would be 3 out of 9. The probability of picking a green ball is 3 out of 10. The probability of picking a yellow ball secondly would be 7 out of 9, because we lost another ball. The probability of picking a green ball after another green ball would be 2 out of 9. When we have a scenario such as this one, to determine our tree diagram, we would firstly take note of the fact that there are 3 possible outcomes. Firstly, we could get a purple heart, a blue heart, or a green heart. After picking a green heart, there is no probability of picking any other green heart. So we just focus on purple and blue. The probability of picking a green heart is 1 out of 6. Afterwards, the probability of picking a purple heart would be 3 out of 5. The probability of picking a blue heart after a green one would be 2 out of 5. We do the same for blue and purple. After picking a blue heart, the probability of picking another blue heart would be 1 out of 5. The probability of picking a green heart would also be 1 out of 5. The probability of picking a purple heart would be 3 out of 5. Now, because of space, I will not continue, but the process goes on and on until we've finished all the contents of the set. Lastly, we will explore the sum and product rules. The simplest way to put this rule is AND means multiply and OR means add. They are applicable in cases where we have independent events, meaning that these events do not affect each other. We will now use an example of heart picking to illustrate how to apply these rules and where to apply them. The probability of having a purple heart is half, or 3 out of 6. The probability of having a blue heart is a third, from 2 out of 6. And then the probability of having a green heart is a sixth. Given that we are asked to pick 2 hearts at once from this set, and then required to determine the probability of having a purple heart and a green heart, we would determine this probability by multiplying the probability of having a purple heart by the probability of having a green heart, because we say that AND means times. So that means we are multiplying a half by a sixth, and that gives us 1 out of 12. If we were to be asked to find the probability of the heart to be blue or green, we would do this by adding the probability of having a blue heart to that of having a green heart. And that means we are adding a third to a sixth, and by doing so we get a half. Kudos to you for making it to the end of this video.